Yeah, let's just post to the event, the Zoom link. Um, okay. So, welcome everyone. Today we are starting off the year with a bang. We've got our buddy Harrison Chase. Hey Harrison, nice to see
Hey
you.
guys, thanks for
The
having me.
Thanks for
CEO
joining us.
of LangChain. We've been chasing Harrison for many months. We stalk him every chance we can get. Yeah, Harrison, I don't know if you remember, but we sat front row. Me and Antje sat right in front of you during one of the I think it was
AI engineer summit,
yeah,
right?
yeah, yeah,
Yeah.
yeah, the SWIC summit. So we will do not let you out of our sights. And the first chance we can get you on here, we did this year. So thanks so much for joining us. I think we're definitely going to start with you. Yeah, obviously. You basically have as much time as you want, and then any time left over, Ansha and I will fill in with our talk on quantization techniques for memory for compute, and then also discuss fully sharded data parallel. These both come from our book, the one me and Ansha and our third co-author Shelby wrote. I have about 50 copies, but here's one of them here. We'll be signing these and handing them out to people at like events coming up. So, but enough about us. We will be sharing this on YouTube on our YouTube channel here. Uh, and I just posted that into the Slack. If you do have questions for Harrison, just post them right into the Slack here. And yeah, so Harrison, go ahead, man. Take it away. Share your screen.
Yeah, absolutely. Thank you guys for having me. I'm going to talk a bunch about LangChain 0.1, which is a new version of the library that we released a week ago, actually. And so I've got some slides and some docs and some other things to walk through, but also, want this to be a fun and engaging conversation for everyone. So if people have questions throughout, please put them in the chat. And then Ansha and Chris, maybe if there's any particularly relevant ones that are worth interrupting, please feel free to do that. And then at the end, if there's any, can obviously take them there. I'm going to start sharing my screen, so I may not be able to see the chat as closely. Um, cool. So yeah, so we released this. I'll go into full screen mode. So we released this about a week ago. And I want to, before touching on what is in LangChain 0.1, I want to touch on why do it now. So the package and the community have grown tremendously over the past year, a little over a year at this point. I think and it's grown in a bunch of different ways. I think we have over 2,000 different contributors to the Python package. We've got, almost 700 different integrations. We've got a lot of different templates and cookbooks. And so as it's grown, we've seen this need for focus on organization of the repo, both conceptually and architecturally. So there are a few kind of like architectural changes that we've made to try to facilitate the growth. And then also a big part of this is just conceptually focusing on a few different areas that we want to be really good at and we want the focus of LangChain to be on. Another reason for doing and announcing 0.1 is we've actually made a lot of changes over the past 6, maybe even 8 months. So some of the things that I'll talk about have been in the works for a while. We've done all these changes largely in a backwards compatible way. And so we've kept around, I can chat more about like LangChain expression language, but we've kept around kind of like old chains, as well as started having more and more of LangChain expression language. And so as we've been kind of like incubating LangChain expression language, and some other newer features as well, we've it's been about 6 months of doing that, and we thought it was about time to kind of like publicize them more heavily and say like this is, we have confidence that this is kind of like the way to do things. Another reason to do 0.1 is basically we saw a lot of people depending on LangChain more. So both companies looking to put it into production, as well as other packages and frameworks that are building on top of LangChain. And so we wanted to give them confidence that the base kind of like interfaces wouldn't change, and that they could extend the LangChain, they could depend on it, they could use it in critical parts without having to worry that any of the methods or any of the underlying base classes might change. And so some of the architectural things we've done have been towards that goal as well. And then the final bit about like why now, and it's a bit risky to say this because the space is moving so fast, but it kind of seems like base APIs of the language models are a bit more stable. We specifically waited until multimodality kind of like was released to see what the APIs would be, to see if there were any large breaking or different changes there. There weren't nearly as many as we kind of like feared, perhaps. So I remember when chat models first came out way back, I guess almost a year ago at this point, that was very different than this is the fun fact as well, actually. The first models that we used in LangChain, the OpenAI models, they're actually removed from the API now. So like almost by definition, it's been a year, but it's been a year with a lot of change in it. And so we've had to change a bunch of things. Some of that, like the chat models, have actually been a large-ish change to the underlying abstractions. And so we were worried that multimodality or other changes might pop up, and they still may. And so, this could be famous last words right here. But we have somewhat of a sense that things are a bit more stable, and so we think it's a good time to release the 0.1. So there's 7 main things that we highlighted as part of 0.1. And so I'll walk through all of these. I have a slide for each, and then for some of them, I'll probably go to external resources as well. So observability is maybe one of the biggest things that we've been focused on. We think it's incredibly important for when you're really building anything, but especially complex, by complex, maybe like more than a single LLM call in your application, and you have a sequence of them. Um, and so we've focused on observability a bunch in a few ways. We've had a verbose mode in the library from nearly the beginning. Shout out to Off Air Press, who he wrote a great paper called Self Ask with Search. And it was an early version of an agent. And he had this verbose mode where it would print things out nice in different colors. And so we really liked that. And so we incorporated that. We then added a debug mode once we started having more and more complex things that would log less interpretable, but more kind of like dense information. We recently added methods to inspect runnables. So this graph that I have on the right is generated automatically from a LangChain expression language object, which I'll talk about more. But basically ways of visualizing these kind of like these graphs that you're creating. And then perhaps the biggest thing that we've done is LangSmith, which we launched maybe, yeah, I think 6-7 months ago. And it's a completely separate platform. On the side, it does a bunch of things, but one of the main things that it does is observability. And so just showing what that looks like very quickly, I have this other tab up here. This is LangSmith. There's a bunch of stuff in here. If we go to projects, these are kind of like logging and tracing projects. So I can click into this. I can see a list of all my runs. And then I can click into a run, and I can see kind of like exactly what's going on under the hood. I'm playing around with some different types of agents, and this is a type of agents where I specifically call a tool first. And so it's slightly different. And so I can see that I'm actually doing that. I'm calling a tool first, and then I call the language model, and that's kind of it. If I go into a separate run, let's see what this one looks like. Yeah, so this one, I can now see that I'm calling a language model, then I'm calling a tool, then I'm calling a language model again. So even these are kind of like simple example of agents, but you can see like what exactly the steps that are happening are. And then if you click into it, it will load like the exact kind of like prompt that's going into the language model. So in this case, there's the first human question, then a function call, then the result of that, and then this is the output here. You can jump into a playground and edit it and play around with it. And then there's a bunch of other functionality that I won't go into it, but the main value prop that I want to highlight here is just observability. It shows you what exactly is going on inside your application. And this is something that again, not only through LangSmith, but through other things in the library, we want to make incredibly, incredibly good. We think it's one of the most important things. I was actually listening to a podcast with Logan from OpenAI the other day, and he said observability was underrated. And I completely agree. It's so important. I use it all the time internally to just speed up development a lot. So this is one of the main things that we wanted to highlight. the second of like the two big things, first one being observability. The second one is the integrations. Like we took this opportunity as well to talk with a lot of people in the ecosystem who use LangChain, who don't use LangChain. And one of the things that everyone said that they liked and what kept them coming to LangChain is basically the integrations with all the different third-party providers and things out there. So we have almost 700 different integrations. These range from language model providers to vector store providers, to tools and toolkits, which you can use with agents, to document loaders to load documents from sources, to managed retrieval services. We've got a lot with Amazon as well. So we're worked very closely with them. And so this is, no one else has this kind of like collection of community and integrations and that's a big reason why we have kind of like over 2,000 contributors, is because we've got a lot of kind of like a lot of community members adding all these different integrations. And so one of the big things that we've done is 0.1 is a different, we've changed up the architecture of how we're managing the package specifically to better enable integrations. So before, all integrations were part of the LangChain package. This, was great because it made it pretty easy to get started. But as we started to scale and have, again, nearly 700 integrations, it became a bit overwhelming. There was like the integration code, and it wasn't clear what the separation between integration code versus core code versus like the chains and agents were. There was sometimes conflicting dependencies between the different integrations. And so, one of the things we did early on was make all the integrations optional dependencies, which was great because it didn't install by default, but then it was tough to know exactly what packages to install, and led to some issues there. And then the other thing is all these integrations, as mentioned, the space is so rapidly changing. All these integrations, the third-party SDKs, they were rapidly changing as well. And so it was really hard to communicate if one specific integration had a breaking change in it because it was lumped in with all the other integrations. So we've done a few things in 0.1 to try to address this. First, we've moved all integrations to LangChain community. So this will hopefully separate like what's an integration, what's core code. One thing we did earlier is we have LangChain core. So that's kind of like the core abstractions. We have LangChain community, which is the integrations, and then we have LangChain, which is the chains and agents and all of that stuff. So we moved all the integrations to LangChain communities. And then we started also creating separate partner packages for some of the larger and main integrations. And we're still early on here, but we're going to continue to add more and more of the main integrations here so that we can version them, so that we can have explicit dependencies, and just generally make the developer experience around integrations, which people say is one of the best things about LangChain, more and more smooth. So observability and integrations are two of the main things that we heard when we talked with people about what we should focus on around LangChain. Jumping into the next few bit, one of the larger changes from a DevX perspective is probably moving more and more towards LangChain expression language. So if you haven't seen LangChain expression language, one of the first values that it adds and basically one of the main motivators for it is this idea of composition. It makes it really easy to compose together arbitrary sequences of things, and then it's largely kind of like a data orchestration framework. So you get a lot of benefits of data orchestration frameworks. So like parallelism, retries and fallbacks, input and output schemas, access to intermediate results, and then streaming support, which I'll talk about later. But LangChain expression language is a new way to kind of like dynamically create custom chains. So we have a whole section on LangChain expression language here in the docs. There's a getting started section that shows what it looks like. So here, this pipe syntax just kind of joins them together. So this would be the equivalent of an old LLM chain. It's a prompt, a model, output parser that you just join together. And so this is a relatively simple example. We also have a cookbook of other examples. So if we look at RAG, we can see that here is a really simple RAG chain where basically we add in context, and then we pass that to the prompt, to the model, and then the output parser. And so the benefit of this is that it makes it really easy to create custom chains. That's largely it. And create custom chains that have the same interface as all other chains, that have the same like the same good logging as all other chains, that automatically get streaming both of final results and intermediate steps as all other chains, that can easily add parallelism like all other chains. So if we compare this to the previous style of things, we had pre-built chains, and they had some of them had these things, others didn't. So, not all chains supported streaming, not all chains supported async, not all chains supported batch, not all chains did parallelism correctly, not all chains kind of like logged all the results. Maybe they logged all the steps. Maybe they logged 3 out of 5 results steps, or something like that. And then a big issue with the previous chains is that they were all their own independent classes, which was great for getting started. But if you wanted to customize them, then you either had to subclass the class, or you had to write your own class, and so it wasn't the easiest DevX to kind of like create custom chains. So a big part of 0.1 is allowing people to create custom chains really easily with LangChain expression language. This was all done in a backwards compatible way. So the chain classes from before are still around. And then we will also add high-level entry points that use LangChain expression language under the hood. So conversational retrieval chain was one of the most popular chains from before. We will add a create conversational retrieval chain that uses LangChain expression language under the hood, that has a very similar interface to kind of like the existing chain. And that way, if you want just the high level entry point, you can absolutely use that. You can get started easily with that. Under the hood, you also automatically get like the streaming, the parallelism, the async, the batch for free. I don't even know if conversational retrieval chain had those things. But then if you want to make modifications to it, the existing chain is just written in LangChain expression language, so you can go in and modify it there. One of the next big benefits that goes hand in hand with kind of LangChain expression language is streaming functionality. So streaming is super important to LLM applications. They often take a while to respond, so you want to show the user what's going on, either at the token level or at the action level. If you're working with agents that maybe take a bunch of actions, you want to stream back those actions that it's taking and the results of those, so that the user can see what's going on. Previously, barely any chains implemented this, and if they did, it was done in an ad hoc way, and you had to re-implement it with each chain class. And so with LangChain expression language, everything created with LangChain expression language automatically gets streaming out of the box. They all have a standard interface. They have stream, astream, and astream log. Stream and astream are basically synchronous and asynchronous methods that will stream the final results of the chain at a token level if applicable. And then astream log outputs this thing on the right here, which is a lot more detailed. And it's basically a log of all the of everything that's happening throughout the chain. We're working on a more user-friendly version of this as well, that's more in sync with the callback handlers that we had before. So this is like maybe the most extreme version. It's everything that's going on. Naturally, some events are more important than others. You probably care more about language model calls and retrieval calls and tool calls and things that we had callback events for, as opposed to if I'm going through like a data transformation step or something like that, because LangChain expression language makes it really easy to add just arbitrary functions there as well. So those could be part, but you maybe don't care about streaming that back to the user. Maybe you do. And so if you do, you can use astream log, but we're also working on a more user-friendly version of this. Another thing that we wanted to highlight in the spirit of kind of like core functionality and core building blocks is basically output parsing. So output parsing refers to taking the output of a language model and then converting it to some more structured format that you can use downstream. And that's super important for LangChain, because a lot of what LangChain is connecting LLMs to external sources of computation and data. And so that often requires having that output be passed as input to a next step, and that input often needs to be structured with certain arguments and things like that. So we have a bunch of different types of output parsers, and one of the big things that we did was we added a nice table of all the different types, as well as some checkboxes on basically what they support. So we did the work of supporting streaming for a lot of this, what the input types are, what the output types are, description of when to use it. And so we think this output parsing is super important for developing these more complex applications. And so we really beefed up both the support here, as well as just the communication of what exists and the documentation around that. The last two things I want to highlight are more towards the use case side of things. So retrieval is one of the main use cases that we see in LangChain. And so we've added a lot there. And I think we have one of the best retrieval modules out there. There's a bunch of different steps in retrieval that go from loading documents to transforming documents to embedding documents to storing them in a vector store or another managed retriever service. And then there's also advanced retrieval algorithms on top of it. And so for all of these, we've added better documentation and really beefed up kind of like the support that we have here. So document loaders, we have about 100 different document loader to load documents from different sources. Text splitters, it's a bit, I don't know if it's boring or not, but it's really important how you split the data that you're working with. And so we have a bunch of different types of text splitters. And this code text splitter supports like 15 different code languages as well. So there's really even more than this. And we've invested a bunch in having a large selection of, I'd say like basic, custom, and then like advanced and experimental kind of like text splitters. Embedding models and vector stores, we have a ton of integrations for. And then retrievers, this is one of my favorite things that I got to work on when working on 0.1. We have a lot of advanced retrieval methods. And so we documented what these all are, when to use them, a description of what it is, what the index type is. So like, are you just storing data in a vector store and then doing something on top of it? Or do you actually need to transform the underlying data storage that you're using? Whether it uses an LLM and things like that. And so I'd highly recommend, we're going to do a deeper dive on all of these, but I'd highly recommend checking out this table for a pretty comprehensive overview of generally what advanced retrieval things are out there. And then this, the indexing pipeline flew a little bit under the radar, but I think this is super cool. Basically, when you're working with real world data, the data is often not just static. There's changes to it. And so how do you sync those changes from their source to the vector store? And do you just overwrite everything all the time? Do you do things in increment? And so we've added a indexing pipeline that has a few different ways of basically indexing these documents such that you can keep things in sync, and a lot of the methods that the overwrite everything or just do incremental, they're indexed here. But we've invested a bunch in basically more production support for some of the ingestion things. And then the last thing that I want to talk about is agents. So I think a lot of people know LangChain for agents. It's a big focus of ours. Agents is also an overloaded word, and so I'd largely just recall this, or I'd largely equate this to using an LLM to take actions. And so a big part of that is the different prompting strategies that you use to help the LLM how realize what actions to take. And so we have about 7 different types of agents that equate to different prompting strategies. Some of them just use, OpenAI function calling under the hood. Others of them have like React style prompting. And so we have a big list of them here and descriptions on when to use them. Another big part of agents is tools. And so we've invested a lot in making it super easy to define custom tools, because one of the big things that we saw is that, yes, we have like 100 different tools that you can use out of the box, but if you're using this in production, most people doing that are using it with custom tools. So we want it to be really easy to create custom tools. And so we've invested a lot in this idea of letting LLMs take actions and call tools. That's largely what I have. Happy to take any questions. I'll also post these 2 things in the chat, but basically this is a blog where we walk through a lot of the motivations as well as details of everything in just more detail. And then we also created a YouTube playlist. And there's 1 video for each of these sections that goes over a lot of what I just said conceptually, but then also has some hands-on kind of like coding things, which I think is a great place to get started if you're looking to get started with LangChain in general, or if you're looking to come back to it after a while and get started with LangChain 0.1. yeah, that's basically what I've got.
All right, thanks so much, Harrison. That was a great tour through all of the functionality. We have a bunch of questions here. Chris, do you want to pick a couple?
Yeah. There was one I thought was really interesting, which is LCEL. Is easy but not so Pythonic. Can you tell us why the team ended up with this design against a more Pythonic subclassing design?
Yeah, I think I mean, okay, so this kind of gets to a big debate between, I guess, yeah, I don't know, object-oriented programming and some more functional programming. We obviously started off with the classes. I think if you look at data orchestration frameworks in general, they often have more of this like pipeline syntax. And at the end of the day, I think a lot of what LangChain is similar to kind of like a data orchestration framework with some Gen AI native requirements, like streaming, like LLM specific observability. So I would say, I think overall we found it to be just a better fit for enabling a lot of custom pipelines, which is what we were seeing people wanted to create. I think object orient the class, the subclassing is great in situations where you have a bunch of things or where you maybe have like a standard interface that you need to implement and you can subclass it and implement that interface. But oftentimes when we saw people creating these complex pipelines, it was less around just like implementing a specific piece of the puzzle and more about stringing a lot of these things together. One thing that I will say is that if you look at the history of kind of like data orchestration frameworks like Airflow and Dagster and all of those good ones, I think our syntax is probably more reminiscent of Airflow like 1.0 as opposed to some of the newer styles of doing things. And so we are experimenting, like I think maybe I can share my screen and just show one thing. Like the syntax, definitely there's a little bit of a learning curve to it. We think it's super powerful once you learn how to do it, but we also want to make it easier to, we just because we want to make it easy to onboard. And so some of the things that we're thinking of are more reminiscent of like the Dagster or the Airflow 2.0 way of doing things. So we have like this chain decorator right here, which basically creates a chain. And then and I think this is very similar to like a Dagster like task thing. And so then in here, you're still, I think the key thing to note is that you're using the invoke, the invoke methods, or you can even chain smaller bits together. So I think like chaining these sequences together, I think that's like fairly intuitive. It's maybe when you have some more kind of like custom logic, it's easier to write it out. And this is what we saw a lot of data orchestration frameworks doing. And so we've done some work. If we think about like why do you even want a data orchestration framework for LLM things in the first place? I think some of the big benefits are observability, and then streaming of intermediate steps and of tokens at the end. And so basically we've done some work to make sure that this chain decorator accomplishes all of that. So everything inside here, is logged through callbacks to LangSmith or to the terminal or anything like that. So you get the same benefits of observability. And then through that as well, we can do streaming. The streaming of the final results depends a little bit on the return type. So if we did a yield here, then it would yield that. But for the stream log of the intermediate steps, we get things back there. So this was a little bit, I don't know if this was completely answered the question, but hopefully that's a little, we've thought a lot about the best ergonomic way to enable this, and that's maybe a little bit into some of the considerations that we're thinking about.
Gotcha. Another, I guess, this llama index, and then LangChain, like what do you see are the differences, or how do they complement each other? When would you use one over the other, or use them together, kind of thing?
Yeah, I think so I think that used to be really easy to answer because I think they were pretty complementary. And I worked with Jerry. I worked with Jerry at our previous
Yeah.
job for like 2 years, so I know him well. A ton of respect for him, like and the whole Llama Index team. I think at the start they were super complementary, right? I think Llama Index was doing a lot of really cool stuff around different types of indexes that you could use. They started off with like a tree index and some of the hierarchical stuff. I think over time, for whatever reason, you know, I think there's more and more overlap. And so, you know, at this point, I think a lot of I think a lot of the focus seems to be on similar things. And so I haven't used Llama Index super recently. I'm obviously biased as well. But I think basically the focus has become more and more the same as opposed to complementary would be my take on it.
And I guess this one's labeled advanced RAG. Is there any module, or is there any thought, I guess, to building sort of higher level patterns like, you know, citation validation, PII redaction, things like that? Yeah.
Yeah. So so for the PII redaction stuff, that's something we actually just did a blog post with Ally, the bank, and it was on the JavaScript library. But basically we added a pretty comprehensive module for doing PII kind of like redaction and filtering there. We have similar things in the Python version. I believe some of them use Amazon services under the hood. And we don't have a formal abstraction for that. Largely, I mean, you know, there's a million things to prioritize, and that hasn't been one of them yet, but we do have functionality there and some cookbooks on how to use it. For like the citation stuff, a lot of that really comes down to like prompt engineering and output parsing that you do. And so we do have some chains built in that do that type of thing. One of the big things that our big focus now actually is on use cases, and on use case documentation. I think we've done a pretty good job of documenting the modules. A lot of the use cases need kind of better documentation. I think, you know, we have a whole use case section on question answering, and one of the things that I forget if we've added it or we need to add it, is this idea of like citation thing. So basically, I would say like use cases are like the higher level abstractions, or the higher level documentation of things in LangChain. And so if you're looking to get started with at a higher level, I would recommend checking those out first. And then if you want to understand kind of like the core building blocks and the underlying modules, then I would go to a lot of the module pages that I was talking about.
And
Yeah.
yes, Antje, go ahead.
Yeah, I think that ties really nicely. And we had a couple of questions from folks. Where can they learn more, right? Is there a hands-on workshop to do the end-to-end use cases? So I think you just mentioned that in the documentation, right? But is
Yeah.
there any specific learning resource people could go to?
Yeah, so I'd say like yeah, so just walking through the documentation, I think like this is if you want to get started with some of the more modular things, I think like this is the docs page here is a good way to do that. And so it goes over LangChain expression language, all of the modules. Then we also have these use cases. And so we're actively in the process of revamping a lot of these. But for example, question answering with RAG, we recently revamped. And so we kind of like have a quick start, a tutorial on returning sources, or tutorial on adding chat history, so it can turn into a chatbot, streaming, per user retrieval. So if you're building a multi-tenant app, using agents to do RAG, using local models. So I'd recommend this use cases page as a place to go if you're thinking, hey, I have this use case in mind, I want to get started here. The other good place is also integrations. So, you know, we have this page with AWS, and there are a lot of different things we have here. And so I saw a lot of questions in the chat, like, you know, can I use this AWS service with LangChain? And so if you have like, if you know that you want to use Kendra Retriever, or you want to use like Amazon Textract, like I'd go here to check out that and get started. And then the last thing that I'll mention is, and a place where we're starting to invest a lot more time, is actually in our YouTube channel. And so yeah, actually I'm very unfamiliar with YouTube. But here we go. Okay, so yeah, we have a lot of resources on here. And so just highlighting a few of the playlists that we have. We have 8 videos on the 0.1 launch that talk about everything that I just talked about. And again, there's hands-on coding there, so I'd highly recommend these. We also have a build with LangChain YouTube channel. And so these are more like 30-minute to 2-hour long videos where we build a full stack application. And so if that's more your vibe, I'd go there. We have a bunch of webinars And then LangSmith, actually the thing I highlighted as well, as I mentioned, there's a lot that LangSmith does besides observability, and so we have a whole playlist for that as well. So we're investing a lot more in the YouTube channel, and I'd recommend that as a place to go to get started as well.
Fantastic.
Great. Eval has come up a few times in the questions here. Do you have any, like, is like LangChain like heading in the whole eval space? And
Yeah, I mean, this sounds like an invitation for a second webinar because there's so much to unpack here. Um, I think eval is probably one of the things that people are trying to figure out the most and uncertain about the most. I actually made some very brief slides for this the other day. And again, this is like legitimately a separate webinar, but I can run through this super fast because I do think this is again probably the thing that people are talking about the most. So LangSmith, as I mentioned, has a lot of things in it. A lot of it is focused around kind of like testing and eval. Important to highlight, this works with and without LangChain. I think a lot of questions that teams are grappling with are basically, what should I test? How should I test, and when to test? And so walking through these a little bit, like what to test. Gathering data is often the hardest part of testing. And so basically the main thing we see people doing is creating these input-output data sets. We typically see people starting with about 20, and they're hand labeling these. These are either the engineers or domain experts. They come up with these data points, they create input-outputs. But then we see a lot of teams adding more over time as they start to get traffic. It's often hard to predict how users will use your applications. And so I think it's really important to be able to take those production logs and create testing data sets from them. And so that's one of the ways that LangSmith can help there. And so that's kind of like what to test. Then there's how to test. These are like the metrics that you're using. Similar to the data sets, these are often really specific to use cases. So we have a few kind of like off the shelf evaluators, but we often see teams writing their own evaluators basically. And a lot of these evaluators use LLM as a judge technique. So they use an LLM to ask basically whether it's done correctly or not. And then also, how do you aggregate? Do you expect all of them to pass, like unit tests in traditional software? Do you expect a threshold of above 70% to pass or not? Do you use humans to basically look at the ones that fail? Do you compare to previous runs, or do you look at them in isolation? And so I think these are some questions people. This is largely framed in terms of questions because I think there's more questions than answers. But these are some of the questions that people are asking. And then another question is like when to test. Do you test on every commit to master, every push to prod, every big release? We see people doing all of these. It kind of depends on what the tests are, what the use case is, and the answer for all of these is kind of like it depends / I don't know. But that's a very brief overview of how we're thinking about it and the types of things that we see people thinking about.
All right. So I think we have a lot of more questions coming in, but in the interest of time here, I think we need to kind of wrap the conversation. If you want to stick around, Harrison, and maybe peek at a couple of questions.
Yeah, I can respond to the chat.
Okay.
I'll respond to the chat.
One last question for you, kind of more on the fun side. What are your predictions, trends, 2024? What's going to happen in the space?
Oh, good question. I think we'll start to see more complex applications actually make their way to production. So things that are more than just a single LLM call. I think the vast majority of things in production are actually a single LLM call. I think we'll start to see that be not like they'll start to be more. I don't want to call these agents. I don't want to call these other things, but I think we'll start to see more and more complex things. I think as a result of that, observability will continue to be super important. And then I'm hearing all these rumors about GPT-5, and I don't know anything. But I think we'll see a lot of new models released as well.
All right.
And more like multimodal and yeah, right, like beyond text. And
yeah, multimodal is super interesting. Again, I was listening to this podcast from Logan, and I think he summed up some of the we don't see a ton of like super successful multimodal use cases yet. And one of the things that he was saying is that GPT Vision's good at high level stuff, but it's not good enough at like positional awareness of a lot of things. Like if you're using multimodal to like try to, I don't know, look at a like understand a website that has a bunch of tables, like you really need to understand like this title is here and the numbers under that equate to that. And it's just, it's still a little bit, I don't think it's good enough. And maybe that will come with GPT-5, but I don't think the multimodal stuff is good enough. But yeah, as the newer models come out, then yeah.
Cool. Awesome, bud. Yeah, I think we covered most of the questions here. There's some, like, does LangSmith install with Helm, and how, Kubernetes, Docker friendly is it, things like that. But
I'll respond in the chat. I'll try to respond
Okay.
in the chat to a bunch of this.
All right. Thanks so much, Harrison. Really, really appreciate taking the time and joining us today.
Thank you guys
man.
for having me. Honored to be here.
We will have you back as often as you want to come. So. Cool. Antje, I think you're going next, right?
I'm going next. Yeah, let me bring up my screen share here. All right, so you should see my slides here. All right, we have 2 more topics. We'll try to be crisp, and probably gonna keep rolling here for a little bit, so folks need to drop on top of the hour. We keep recording this, and the recording will be shared again on our YouTube channel. But let me start here by saying again, thanks for everyone who already bought our book, looked into. I saw a couple of feedbacks here on the chat as well. Chris and I and another colleague of ours, Shelby, we published the book Generative AI on AWS in December. Super excited about it. We are also super thrilled that we hit a number of #1 new releases actually on Amazon.com. Chris put it on here: cloud computing, natural language processing, AI, etc. So really excited to see this feedback from everyone, and we hope you enjoy the book. What we're also gonna do here, just a quick call out maybe also to our reviewers. We shared the book with a couple of people that helped us, review everything, and a big shout out to them here also to do that. Any words from you, Chris?
Yeah, no, these people were great. Brent helped us on the first book as well, brought in some other folks like Randy Defoe from AWS, and also outside to people like Gita, who has been a friend of ours for a few years now. So yeah, these people were absolutely pivotal.
All right. Now let's jump into the next 2 topics we have for today. We're going to talk about quantization and memory optimizations for large language models and models in general. We'll also talk about efficient multi-GPU compute strategies. So quantization, I will actually show you a little bit more what that entails. And then also we're going to have a discussion, what if I can't fit even quantizing a model on a single instance, on single GPUs anymore? And then Chris will take the discussion to go further into talking in general about the strategies, but also zooming in a little bit on the fully sharded data parallel FSDP strategy. All right, and with that, let's jump right into it. So let's start with quantization and memory optimizations. And if you've worked with LLMs and if you've worked with NVIDIA GPUs, you most likely have seen this error message here. CUDA out of memory. So one of the most common issues you'll encounter when you try to train large language models is basically running out of memory. And libraries such as PyTorch and TensorFlow all use the CUDA libraries here to help boost performance. But many times you probably have this error popping up, including me. So let's talk about some of the reasons and how you can actually avoid that or mitigate running into that error. So let's talk a little bit about how much RAM is actually needed, how much memory is needed to load and also to train a model. So let's start looking at the different parameters here. So if we do a little bit of math just to build up the intuition, a single parameter is typically represented by a 32-bit float number, and one 32-bit float takes up 4 bytes of memory. So if you store 1 billion parameters, you would need 4 bytes times 1 billion parameters, or 4 GB of GPU RAM if you save it in 32-bit full precision. And that's a lot of memory, right? So, and that's not all. If you want to train the model, you also have to plan for additional components that take up memory. And this includes 2 times the atom optimizer states, that includes the gradients, that includes activations, and also temporary variables that are needed by your functions. So altogether, this could easily lead up to 20 extra bytes of memory per model parameter. So what can we now do to kind of mitigate this? And if you look at this, you would actually need up to 6 times the amount of GPU RAM, right? Compared if you train a 1 billion parameter model, compared to just storing, loading it. So what can we do? And here's where quantization comes into play. And let me just walk you a little bit through what's happening here if you quantize. So let's start with the floating point 32 numbers. And what happens is if we quantize, we are projecting that number space into a lower dimension. So looking at the floating point 32, those numbers have a specific number range, right? So they go from negative 3 times 10 to the power of 38 to 3 times 10 to the power of 38. And if we project them to a lower dimension space, for example, for FP16, I'm going to touch on the different data formats here in a sec too, bfloat 16 or integer 8-bit, you need to kind of find that new range to represent that number, right? So you lose a little bit of the precision, but this is basically what quantization does. So statistically projecting this original 32-bit floating point number space into this lower precision space. And for that, it needs to have some scaling factors that are calculated. All right, so let's look at an example. Let's assume we're going to store the number pi. And here's the example. Let's actually store it just to 6 decimal places. And then I'm going to store this in different precisions so we see what's happening here. And again, probably most of you know, floating point numbers are stored as a series of bits, so zeros and ones. And here you see how this short number of pi with the 6 decimal places looks in FP32. And what happens here is we have 1 bit for the sign, where 0 indicates a positive number and 1 indicates a negative number. And then we have 8 bits for the exponent of the number and 23 bits that is representing the fraction of the number. And the fraction is also sometimes referred to, you might have seen this as a mantissa or significant. And basically what it does, it represents the precision bits of that number. All right. And if we look the original number here, and then you see that we lose a little bit of the precision if we convert that into a specific space, even if we're using like the 32-bit floating point. All right, so let's have a quick look at what this looks like if we do FP16. And this is a 16-bit number, so it's a lower precision space. And you can see here that we still have the sign bit, but we do have less bits for the exponent, 5 bits, and we do have less bits for the fraction here, 10 bits. And this means we have less numbers we can represent, and FP16 goes from the negative 65,504 to that positive value. Now, FP16 helps us save memory footprint, right? Storing numbers in FP16 cuts down the memory requirement in half. So we only need, instead of 4 bytes for FP32, we need only 2 bytes here. So it's already helping us to reduce the memory. But also it comes with a loss in precision, right? So the research community has explored a couple of more options. What can we do here? And one option that is pretty popular is bfloat16. bfloat stands for Brain Floating Point Format. It was developed by Google Brain, hence the name. And this one has become really, really popular in the space, a really popular choice in deep learning. And we're going to see here why. So bfloat16 is basically a hybrid between the half precision FP16 and the full precision FP32. And that helps you with training stability. It's also sometimes called the truncated 32-bit float, as it captures the full dynamic range of the full 32-bit, but only uses the 16-bit. And you can see here that the bfloat16, it uses the full 8 bits to represent the exponent, but truncates, hence the name, the fraction to just 7 bits. So to summarize here, it helps you to save memory, but also it helps you to increase the model performance and helps you to speed up calculations. And it's, as you can see here, it almost preserves that original range of FP32, which is the exciting part about bfloat16 as well. All right. The other option is let's quantize into an integer space. And there's a couple of different options out there. 8-bit integer, we've also seen 4-bit integer that's being used. And here, again, similar idea. You basically find that range in an integer space. And here, if we're going to store pi, it's coming down to having 1 bit for the sign and then 7 bits for the fraction. So I guess no surprise, if we quantize the number here into the integer 8-bit space, it's going to be projected to the number 3. All right. And we do have a smaller number space here, but then again, it helps us again with the 8-bit to save memory. But it is a pretty dramatic loss of precision. So we always want to make sure when we're doing and do quantization that we still kind of preserve the accuracy overall that we want to achieve, kind of our SLAs for the model. Okay, here's a quick summary. Again, at a very high level, our book goes in much, much more detail here and discusses the different options, the pros and the cons. But again, quantization, we're projecting the 32-bit full precision into a lower dimension space. There's different variations, but you can see that we're cutting down the memory pretty dramatically. Instead of the 4-bit for one parameter, we now either go to 2-bit or even less. And bfloat16 actually has become some of the most popular choice in this space. And for example, Flantify, Falcon, Llama 2 have been pre-trained with bfloat16, just to name a few. And overall, again, as I said, reduce the required memory, projects the numbers. And then there's different ways to apply quantization. There is what we call quantization-aware training, QAT, that learns those scaling factors, how to project the numbers. And then bfloat16 is definitely one of the popular choices. And if we now bring this all together and look again at how much approximate memory is needed, again, we had the 4 gig here at full bit precision, 32, and then we're cutting that in half for a 1 billion parameter model to just 2 gigabyte. And we could also cut it like even further to just 1 gigabyte at 8-bit. And similar, if we look at the training part where we need to have more memory footprint, we can see that with a 1 billion parameter model, that helps us to kind of, reduce the memory to train maybe on a single instance on a single GPU. But definitely, if you're looking at today's models, right, they're way larger than just 1 billion parameters. So for example, if you look at a 175 billion parameter model, at 32-bit full precision, we would need like in the thousands, sometimes if you go further in the model parameter size, tens of thousands of gigabytes to store and train the models. So this is definitely not feasible anymore on single GPUs. So you will need to split your model across multiple GPUs for training. And this is where the compute strategies come into play. And where I'm going to hand over to Chris, who'll walk you in the remaining time through those compute strategies. I'm going to deep dive into specifically the fully sharded data parallel as well. All right, Chris, I'm going to hand over to you.
Okay, cool. And I do want to call out, I'll paste it here into the chat. There is support, well, not specifically, but there is SageMaker support for this algorithm called Smooth Quant. And this is literally, I don't think we have an example offhand, but you can essentially say use Smooth Quant equals true, and that kicks in. So that's something pretty interesting that'll show up in some of the SageMaker APIs. Let me share my screen and get the deck up here. A couple questions in there, Antje, as well too. Let me get rid of my calendar here. It's painful to look at, especially on a public holiday. Okay, Zoom, share screen over here. Okay, so this is where you left off, right, Antje?
Yes, right.
Okay, right on. So we're going to talk about a few of these efficient, what we're calling multi-GPU compute strategies. Now, multiple GPU can be a single instance with multiple GPUs, or more interestingly and increasingly more and more, where we actually need to have multiple of these instances. So if one GPU has, or if one instance has 8 GPUs, that's often not like enough to do some of these larger pre-training. You know, we work with a lot of customers who are actually pre-training foundation models on their own and you know, from scratch, and so they need to extend beyond a single instance. Okay, and so if the model is too big for a single GPU, then you know, that's when we actually need to switch to distributed compute. So you know, like pretty obvious. Now, there's this technique called distributed data parallel, and distributed data parallel, if you have ever used Spark or you know, anything like that, that's really, you know, what's happening here is we are able to split the data up and put them onto separate you know, nodes or separate GPUs. And so this is a pretty straightforward and well understood concept. What's happening here is we take one slice of the data, put it onto each GPU, separate slices. We do the forward pass, we do the backward pass. We then synchronize across those GPUs. There's the step to actually synchronize those gradients, what was learned, you know, during the forward and then backward pass, synchronize, and then we go and then update those model weights that are within each of the GPUs. So as you can see, each GPU actually has a full copy of the model itself. Okay, now that breaks down when we have these 175 billion parameter models, or you know, 70 billion parameter models. These things can get very large, and so even if you are using quantization, there are still times when you can't store the entire model and all of its weights and all of its activations and you know, the optimizer states into a single GPU. And so that's where this technique called fully sharded data parallel, this is often referred to as FSDP, comes into play. This was motivated by this paper called the Zero paper, and came out of Microsoft. And you know, really these like techniques have spawned from this paper here. So really cool paper to check out. this is, I think, the same chart Antje showed. This is also in the book, of course, too. Each of these model parameters at full 32-bit precision would take 4 bytes. So this is just the actual model weights, the model parameters. Then you add in all of these extra things that are needed during the training, the optimizer states, the gradients and activations, temporary variables, all this. You can actually get up to 20 extra bytes per parameter. So 175 billion times these extra 20 bytes. This really adds up, and now you have 24 bytes per parameter, which is really blows this thing up. Okay, and I did code these here because we're going to use this in the next couple slides. So in DDP, which is the distributed data parallel, this is sort of the simpler technique, right? You store all of these on each GPU, and it's an exact copy, and they get synchronized every pass through. Now, we need to split these up across the GPUs once these models get larger, like I mentioned. So, and there's really what's 3 stages here. And essentially, each of these stages, we're storing more and more things. So stage 1, for example, we are only sharding the states of the optimizer. So that's what's in green there. Stage 2, we are also adding in the gradients. Stage 3 is where we are sharding all of these values across all of these GPUs, okay? And so this is in addition to actually sharding the actual data itself, splitting that data up and then placing them onto separate GPUs. All right, so this is distributed data parallel once again. Now we're going to switch to this fully sharded data parallel, and we'll see where we actually have slices of both the model. So this is just showing the model, but also keep in mind that there are still the slices of the data being passed to each of these GPUs. Forward pass, synchronize, update the model. Now this is fully sharded. So the unique thing about fully sharded is because we have slices of what the model needs each time it goes through the forward pass and then backward pass, we only materialize or combine or sort of gather what we need on demand. And so all of these slices come together from the model. And that's this, we're sort of oversimplifying it by saying get weights. This is actually getting all of the data that's needed by the model. And typically this happens per layer. So as each layer is being processed, all of this data from all of these GPUs comes together on demand, but it's just what's needed for that particular layer, not for the entire model. And so this gives us a nice balance of we can use less GPUs, but we only materialize the full set of this data when we need it. And then once we're done with the forward pass, all of that data goes back to each GPU. And then when we're doing the backward pass coming back, we would collect just what's needed again, just for the backward pass. Once that happens, we then synchronize across all of these models or these separate model states that are in each GPU, and all the gradients get synced. And then this happens over and over and over again. So fully sharded, I'll explain a bit more about what the fully sharded does. So it helps to reduce the overall GPU memory that's being used. So this way we can actually effectively operate on much larger models than we could if we had to store the entire model into each GPU. And to give you an idea here, GPU memory is much more scarce, obviously, than CPU memory. So 80 gigs would be actually pretty good. That's on the A100s. On the second sort of generation of the NVIDIA A100, the new H100 actually has up to, well, no, the H100 actually still has 80. The H200 that's coming out this year has, I believe, up to 140 gigabytes of RAM per GPU. Okay, so still pretty limited. Still, things are not quite doubling. We're going from 80 to 140, but obviously the more GPU RAM, the better. And there's also, and so you can offload to CPU. Now, this is not ideal. There's also ways to control the sharding factor. And so let me show here with if you want no sharding to happen, so basically back to the original DDP, right? Which we're calling full like replication. That's the other way to look at this. If you're not sharding, then you are replicating the entire model, all of its states into each GPU. You would set this sharding factor to 1. You can then, if you want the full sharding, which is fully sharded data parallel, which is what we were just describing, you would set it to the maximum number of GPUs. You can also do this sort of hybrid where you're saying, okay, I have 8 GPUs. I don't want to necessarily use all 8 GPUs for this, so I'm going to set it to maybe 4 or something. So these are the different states. I'll show how this translates into code here in a sec. But real quick, so this comes out of this paper, PyTorch FSDP. This is a really, really good paper, experiences on scaling fully sharded data parallel. And it's a specific to PyTorch and talks about some of the design trade-offs and how they ended up developing FSDP. And so here's the different model sizes. Relatively small model. I think this is the Flan T5 series. This is the small version. 611 million, up to the 11.3 billion. So here we see full replication, green, that means no sharding. The blue means fully sharded. And if you notice, the green drops off. There is no way to do fully replicated with the 11.3 billion. And so green drops off here, and then the red also drops off. So, right, like DDP is actually red and the green are basically the same thing. So saying full replication, which is no sharding, is the same thing as DDP, as the non fully shard. So basically the summary here is we need to switch to either full sharding or to hybrid sharding once we get into these larger models. And this is a relatively small model here. This is only like 11 billion. All right. And there's not much of a drop, by the way. I think the estimates from some of the papers that we were reading summarize this in the book as well. It's approximately about a 7% drop for the GPU communication overhead. So that's one of the downsides, obviously. If I back up a few slides here, there is inter-GPU communication happening here when we're sort of like materializing the shards from these GPUs per layer, okay? But it's like overall, I mean, so number one, you have to do it because you can't even fit these into these GPUs, into one single GPU because of the memory limitation. And so taking a small hit, around 7% hit, because of the communication is actually not that big of a deal. I do want to note also with the new H100s and specifically on like like within AWS, this is our P5 instance type, P548XL. The networking has gone from, I believe it was maybe 800 gigabit per second to 3.2 terabit per second. And so now that the networking between these nodes, right? So if I have multiple instances, we've got really, really fast networking going on these P5s. And a lot of this sort of inter-GPU and inter-node communication gets like quite a bit better and faster. So that's actually one of the biggest advantages and why we're seeing customers, move to the P5 is not just because of the, there's more GPU cores and it's the next generation of these GPUs, but also the networking is super fast between those nodes. Okay, the way that hybrid or that sharding factor shows up in code, specifically within SageMaker here, is you set the sharding degree. And this ends up being the total number of GPUs that are in your cluster. And so if you have two, this is actually the P4D 24XL that has 8 GPUs each. You would multiply the number of nodes that you have times the number of the GPUs, and that's going to be 16. And that ends up being passed in to SageMaker here. SageMaker has these things called estimators. That's the main abstraction here when you're going to do any training or fine tuning. You would give it a train.py, which I'll show in a second. And you then provide it the type of like distributed training that you want to do. FSDP falls under what's called model parallelism because we're splitting up the model and it's various states across the GPUs. We're going to turn this on, set it to true. We're going to say DDP true. And then also we're going to set the sharding data parallel degree, which is also called the sharding factor. And that'll be set to 16. And that then turns on FSDP. Now, train.py does need to change a tiny bit. You basically have to, there's this SMP. So this is our SageMaker model parallel library. You would call the init here with the sm config. So these all come from the estimator that was set up here. So these get passed in as basically hyperparameters that end up as args, and you can then refer to them as args. And then there's one other step here where you have to wrap your let's say Hugging Face model here in this SMP distributed model. And the rest of it's pretty straightforward. This is just a regular training loop here, and returning the loss. So I think that's it. Pretty whirlwind here. We're about 15 minutes over, right, Antje? Anything we should discuss here?
Yeah, one question here, like you mentioned, full replication versus sharding, hybrid sharding.
Mm-hmm.
So why would anyone do the full replication, right? And what's kind of the downsides and how to choose?
Sure. And so this shows right here that full replication would minimize the amount of GPU, or the GPU communication that's going on. So full replication is just simple distributed data parallel. And yeah, Antje, I remember you and I, while we were reading these papers and speaking with customers, we would always have to create kind of a little data dictionary of, okay, some papers call it fully replicated, some call it,
Right.
just distributed data parallel. So this is fully replicated distributed data parallel. And there's, so when you switch to the fully sharded or hybrid, you now need to do this materialization that happens. So think of it like each GPU has part of the layer that you need. That's where the term model parallel comes in, and those have to get combined before they can actually be used, right? Because if you only have part of the story or part of the calculation, you have to combine all those parts to get one full layer. So yeah, there is a bit of overhead, but yeah, like I said, as these models get larger and larger, there's really no other choice. And that's assuming that you've exhausted all of the quantization techniques that you discussed. And yeah, so
right.
there's, yep.
Bonus question, Spark. I know you have a strong Spark background. Loading parallel data from Spark or databases is the main problem. Is there any method to load features from tables in Spark in parallel?
Oh boy. There were various attempts at this throughout the years. I used to work at Databricks, and so I keep an eye on what they were doing here. There were some older libraries called Tensor Bricks or something where they would try these kind of things. When you're doing model training or model fine tuning, you want to minimize the amount of sort of online retrieval, right? And we spend a lot of our time getting customers data. We use Spark to get the data in a format that we then save onto S3 and then train off of S3 where we can pull in parallel and do a bunch of tricks there. I think so. The short answer is pulling from Spark and using Spark for these more sort of modern training techniques is probably not the best idea. There's a lot of work that's been put in and actually was just released, I believe, during reInvent timeframe for like Amazon, optimized ways to load data. Like there's a custom PyTorch loader now that can load from S3 in a very efficient manner. But yeah, haven't seen much recently on the Spark front. There were various attempts, but didn't quite pan out from like what I can tell. Is we're entering the hyper. Yeah, we need to have parallel loading from Spark PyTorch distributed mode. Yeah. So this person still asking about Spark. Yeah, that's interesting. Haven't revisited that in a while. What was the other question? Can I use OpenMMT? Okay, is there any hands-on workshops to do end-to-end use cases? Right, I think that was a question that came from the LangChain talk for the hands-on workshop. We have quite a lot of workshops that are not specific necessarily to AWS, but they happen to use, SageMaker Studio and things like that. So, Antje, do you have the link to the catalog of workshops? I have it here, actually. This is the link to a bunch of workshops that are built by folks on my team. Oh wait, that's not the actual catalog though, is it? Yeah, if you search around, there's tons of like public workshops that fall under our workshop studio. And workshop studio is just a fancy term for a collection of workshops. There's no like official product called workshop studio, really. You can run these on your own within like your own environment as well. Okay, yeah. And Antje, did you post the link to the PyTorch FSDP Gita paper?
I posted the link to the paper and also the smooth Quen paper.
And the smooth, okay.
Yeah.
Oh, gotcha. Here's the FSDP paper. Yeah, this one, so yeah, this paper here, if you read it, it uses some slightly different terms. Like most of the industry like refers to everything as either model parallel or tensor parallel. And like this paper really kind of opens up your eyes to, okay, like you don't have to start thinking about it that way. Like let's start with the actual problem. And then they work their way into FSDP. But I think we did a like pretty good job within the book to explain this and have some like really good visuals here and stuff too. So, okay, I think we should wrap it up, huh?
Yeah. All right.
So thanks everyone. Here's the links to the book. There's a GitHub repo here that has a ton of examples that support the book as well too. And do we know what we're doing next month, Antje?
So we're going to talk about instruction fine-tuning, continued pre-training, and we're probably likely going to have a guest speaker too again. Gotcha. I think this year we're going to really kind of double down on startups within the Bay Area here. I have a new role within AWS now where I'm specifically working with Gen AI startups. And we're going to try to get some of those folks to come on each month. And also, I think we're going to try to cover Slurm at some point in the next couple months. Is that right? That is right. Yeah. So the startups that I work with, they pre-train their own, like these massive models. We're, what we're realizing is at the cornerstone, a lot of these folks are using Slurm. And Slurm is something I didn't have a whole lot of experience with before sort of last year, and really ties into this new product that we launched at reInvent called SageMaker Hyperpod. And, Hyperpod is really designed,
to get you into these like instances quickly, these P4 instances with the A100, P5 with the H100, and soon the H200 with is it, yeah, H200, or I think the GH200 something. And you can install Slurm on there. You can install the SageMaker libraries if you want, or you don't even need to install the SageMaker libraries. You just get in, start running your PyTorch distributed training jobs, and it's got all the optimized networking. And really, what I love about SageMaker HyperPod is it's kind of back to basics, is the phrase that I use, and it's really giving these folks that are coming out of the research labs and then getting funding, it's really giving them an environment that they're used to. And I'll post a link to a really, really cool workshop if you do get a chance. There's this HyperPod workshop. This is something I'm actually going to be working on later today, and I'll be doing number 3 there. So I think either next month or in March, we'll have one of our like the applied scientists here from AWS that helps out with the like HyperPod customers, and he's going to show us the basics of Slurm, also how to do Slurm debugging, and when your job appears to be stuck, how do you find out what's going on at scale. So thanks a lot, everyone. We'll post this soon, and we'll see you next month.
Thanks, everyone. Bye-bye.